Welcome to our seminar, Horizons of Science. Welcome to LVIV, to those who attend online. Welcome to the Ivan Franco National University of Lviv. We are in one of the lecture halls of this university, those who are in person. And the rest I see from in different places in different countries. Today we will have a talk by Franco Vazza. That's about natural sciences. That's about philosophy, that's about computational physics, I would say, very existential talk. But before presenting the speaker, may I say several words about our seminar? The seminar is kind of example of self-organization. We emerged some 20 years ago. It was the initiative of scholars from several universities and academic institutes in Lviv. And we started to meet now and then, and now it is regularly, monthly, discussing problems of common interest between scholars who work in different fields. And 2 years ago, one more initiative appeared in Lviv. It is Lviv Society of Scientists. It was initiated by Ukrainian Catholic University in Lviv, and it is supported by Simons Foundation, so now we are even more numerous. The reason of today's talk is because of field of astrophysics, which is known in Lviv mainly due to scholars from Astronomical Observatory of National University of Lviv, led by Professor Novosadley. And to say more about today's talk, I would say that even our mass media knows already today's speaker, because some time ago in our newspaper Zbruch, it was a paper about research made by Franco Vazza in collaboration with neurobiologist Alberto Faletti, where networks of cosmic web and networks of neurons in human brain were compared. And may I ask now Dr. Maxim Tsish to say more about today's speaker.
Okay, hello. So you hear me? So with great pleasure, I would like to introduce you Franco Vazza, today's speaker. He is my supervisor and colleague at Bologna University. Short story, I'll try to be short, about how we meet each other, how we met each other. So we kind of knew each other through our papers, because as Professor Holovac just mentioned, there was a famous paper by Franco and his colleague. And in that paper, they cited our paper, which was about cosmic web. So later, when after beginning of full-scale invasion of Russia into Ukraine, volunteers organized a recurring email to connect Western and Ukrainian scientists. So a lot of new bonds appeared. And in one of such emails, Franco actually saw me, and he wrote to me, or was it I? I think it was Franco. And then he proposed me a position at Bologna University. So he made them to make kind of bureaucracy miracle, so I could actually work there distantly. And what I am doing for 3 years now. And I'm not only Ukrainian scientists who got help from Franco, also Anton Rodakovsky here, and we are not only scientists, not only even astrophysicists who got help from Bologna University. Also Lena Trubanyuk works there now, and Bologna University actually helped a lot of Ukrainian scientists. I think it's more than 10 people. It was very important in the beginning of the invasion because chaos was everywhere, and Bologna University actually saved a lot of people, not only putting them into safe place, giving them possibility to evacuate from war in Ukraine, but also keeping their jobs, so they continue to do the researches. There are historians, economist scientists, cultural studies scientists who moved at least for some time to Bologna. And in my case, it also saved, I can say it saved my academical career, because here in Ukraine, we had a cut off scientific budgets in the beginning of war. It's easier now, but still. Europe, in especially Italia, and especially Bologna University, especially Franco Vazza, really was saving our lives and our work. And really, really big thank you for that. Now, actually, a few words about Franco study. So Franco is leader of the top European Union group that studies magnetic fields, cosmic magnetic fields, and radio observation and of galaxies, and also simulation of galaxies. So he's an excellent scientist, but he also put a lot of effort into popularization of science, and he also has a special interest in interdisciplinarity studies, and he will talk about one of his studies today. But again, maybe final and maybe the most important part, I would like to underline that during this time, Franco became a really huge friend of Ukrainians. Not only he was helping me and other Ukrainian scientists, but he also was advocating Ukraine voice in conferences and publicly supporting Ukraine in times of the civil invasion. So we will be grateful for that till the end of our days. Special thank you to you, Franco. And now I think we can start, and I give microphone to Franco. So welcome, and let's start.
Okay, добрий вечір. Дякую. I am overwhelmed, sorry. I cannot actually share, to be honest. I am not allowed to share. 1 second. Just tell me when I can.
What happens? You cannot share, right?
I cannot. The host. Okay, now I can. Now I can.
Okay, right. Thank you.
Okay, and let me start.
Okay, we see.
Yes, and 1 second. I want to
Before you start, usually we allow some short questions in the course of talk. Do you agree on that? Or
Sure, sure. Yeah, yes.
So then when I will see that somebody raises a hand, I will interrupt you. And
yes, because I don't see the small hands.
Because you don't see this, I know. Yeah. Thank you.
Exactly. Okay. So just a few words before. So I'm very pleased to speak about this topic. Also because I put it on the archive, on the public repository of scientific papers early this week, and I'm going to show you it's part of an accepted paper. This is not my main job. I'm a little bit concerned that this is really not my main topic. I do normal, hopefully decent astrophysical research. I'm simulating the universe, the cosmic web, with the particular goal of predicting how the magnetic fields would look like connecting galaxies, what we see already, to what we don't see already, but maybe we will see in the near future, for example, thanks to the square kilometer array, so a very big radio telescope. And this is my daily job. I like to do also a lot of visualization or simulation because they are really nice. Sometimes they end up in the cover picture of some papers and journal. And this is my main brand. Every few years, I also like to maybe just randomly to do papers on something which is connected to that, but is going beyond that. And as you mentioned already, in 2020, so actually during COVID, I did this paper with a neurosurgeon, friend of mine, actually a schoolmate of mine, which is now a neurosurgeon, and we did a paper in which we compared structures of the human brain and on the cosmic web in a quantitative way using Fourier transform, network statistics, etc. I'm not sure scientifically it's so much worth of a paper, but surely it went viral. And at least it is worth for the fact that, as Maxime has mentioned, we established connection just because of that paper, because I started learning and got interested into network analysis of the cosmic web through that paper, because I had a reference list to fill in that paper. So as a part of this, as my daily job, I'm also doing, for example, this is a paper that Maxime already published a couple of years ago, which is the network analysis of the cosmic web. And as a part of our daily job, we produce different copies of what the universe could look like using mathematical methods. I will tell you a little bit more about that later on, but it's normal in astrophysics to produce copies, digital copies of the universe at a very big scale. What you see here essentially are galaxies. And then we try to guess which of these simulated universes is more alike the real one observed through telescope. And then we try to understand which physical models are more realistic than others. This was already a paper done by Maxime, is doing others. This is instead on the right is a new project I'm doing with Anton Rudakowski instead at the Theoretical Institute for Theoretical Physics in Kiev. And it's the same story. This is a new suite of cosmological simulation. In this case, there are 16. There are tiny variations. Some of them you wouldn't even spot by eye, but using quantitative estimators we can. This is also, by the way, called the Makitra suite, because we are trying to mesh together different ingredients, and we are trying to understand better what's reality. Okay, so that's the daily life of a theoretical astrophysicist. However, after a while, you get interested into the following question, and now let me go here. So, as a job, we are producing simulation of the universe. Can this universe be itself a simulation? This is a very generic question. This is not the most immediate question I was posed to myself, but as you might know, this is coming up several times in the popular literature, in media. Sometimes some VIP person is bringing this up again, and people start talking about that. You can really see waves of people speaking of this topic, not in a very scientific way, in the literature. So the question we might ask, which has to do with philosophy, because it has to do with the concept of reality, is this universe, or can this universe be a simulation? What if the universe we are living in is maybe just one of many simulations that someone else is producing, maybe looking at plenty of screens at the same time, drinking coffee and listening to music? What if this is part of a video game? We think we are living in something extremely sophisticated. We do quantum mechanics, general relativity. Maybe these are just the rules of a video game that a teenager somewhere is playing. What if there are many copies of similar Earths or similar universes? They can be same rules, just different games in the same video game, different matches, say. Or if each of these Earth is slightly different, there are slightly different rules. What if the final simulator of all this is not even a human? It's some super intelligent entity which is running all this. Okay, this is the part of, if you start embracing this argument, this possibility, then you can imagine the possibilities are branching out very, very fast. There is no limit. If what we call the reality is something simulated, there is no end of the layers, of the levels of simulation you can think are behind every perceived reality. So this started actually, I was starting thinking of that in a serious, into quote way. Last year I was invited to give a talk into my former Astro Amateur Society, when I actually started doing CCD observations of galaxies, etc. some 30 years ago. They asked me to give a summer talk, a public one. I wanted to be entertaining, so not maybe the usual, the universe is big, galaxies are beautiful thing. I tried to go in that direction. Also because in those days, there were again in the literature some of these evocation. This is in Italian, sorry. This is the same in English-speaking media. Sometimes some VIPs like Elon Musk, which I dislike for many reasons, this one included, is waking up and say, yeah, maybe we're living the simulation, and everybody is following this lead. Very famous popularizer in science like Sabine Ossenfelder here. She did a long video a few years ago. There are also very cool and interdisciplinary debates, like this one was the 2016 Isaac Asimov Memorial Debate in the US, and there were many scientists and philosophers debating about that on stage. There are books, serious one, less serious one. The serious one here is probably the one from David Chalmers, for example. So this is fascinating, and it also started with movies. So probably each of us have seen this very famous one. It's not the first movie, of course, that is using this hypothesis, but it was really a blockbuster. It's very well done, by the way. Is The Matrix. So in The Matrix, I hope I can spoil a movie from 25 years ago. Basically, the reality the main character thinks he's living in is actually a simulation produced by his descendants. So essentially, we are in the future, and the descendants are simulating the past. They are not doing that for scientific reason. They are doing that basically to keep human busy. But so the setup here is that it's the same universe with the same law. There is still planet Earth, but the reality is actually far in the future, and the future is simulating the past, okay? And the humans connected to machines, they cannot tell the difference, except, okay, someone has broken outside of the matrix, and it can lead those people to see out the matrix what it really is. The matrix is a matrix of digital numbers, which are producing a simulation, okay? This is a very fascinating way of illustrating this process, because at some point the main character wakes up and he discovers is not in the perceived reality anymore. Philosophically, this was actually put in a serious paper by philosopher Nіком Bostrom. I don't know if the same paper became very popular because it was basically the same years of all the Matrix series of movie. There were actually other science fiction movies or books before that using the same hypothesis, but Matrix was the famous one, and this one is a paper everybody is referencing to. Are you living in a computer simulation? 2003. So it's a long paper, and it's complex. It also uses statistical or pseudo-statistical reasoning. According to the paper, one of these possibilities must be realized in the future, according to the main author. The first hypothesis is early extinction, like humanity will just disappear in the future before being ever able to produce very complex simulation. It might have sounded a bit extreme in 2003. I'm not sure it's so much extreme in 2025, considering the world we are living in, but that's one hypothesis. The second one is that humankind will evolve, but no one will be ever interested in running complex computer simulations. The third one is our descendants, so humankind will evolve, the access to computing, energy, resources, the curiosity for science will always increase, and our future descendants will basically have infinite or a very large computing power to continuously simulate reality with increasing degree of realism, and they will produce basically an infinite number of complex simulations. They will be interested in simulating their past, so there will be an infinite number potentially of universes of simulated reality in the future. And his pseudo-statistical reasoning here is that there will be so many. So if the third options in the future is the one that is realizing, in the future there will be many more very realistic digital copies of reality, and the chances that we are living in the only possible reality and not in one of the infinite future, very realistic realities is very small. So his reasoning was there will be a numberless amount of simulations in the future which are simulating the past. So according to Bostrom, it is very likely that we are already within some sort of ancestor suite of simulations in which our future descendants are simulating the past to understand, I don't know, historical pattern, evolution of life, whatever. This is the upsetting future scenario. There is an infinite amount of simulation which are very realistic, which exceeded some hypothetical threshold of complexity in which they can form sentient digital beings, and it's much more likely that we are already within one of those simulations because their number is going to be infinite and our reality is just one. This is the argument. It's not really so much of a strong argument, I would say, even if it went viral as well. I mean, it's an interesting line of thinking. No one has ever showed so far, and there are reasons to think it will never be done, that you can just form something which is self-conscious just using digital representation. So far we only know, strictly speaking, only each one of us knows to be self-conscious. It's reasonable all other human beings around us are. No one has shown that you can, if you code a very complex code, that thing can be self-conscious. Maybe only currents in neuron network arranged in a given way can produce that. We don't know. But the assumption is if I just have a very complex computer program simulating a brain, that will also give rise to self-consciousness, and the being in that simulation will think they are in the reality. Okay, that's the starting idea. Okay, so this can be mind-blowing if you want. And many people are continuously shocked and intrigued by this hypothesis. Okay, now, since not only astronomers are here, maybe not only physicists or scientists, let me give a short overview of why simulations are so important in astrophysics. I am a numerical simulator myself. So we do simulation in astrophysics because we can basically do no lab experiments. So sometimes we can record cosmic rays, and I will speak of them, entering our own atmosphere. We can directly detect them. We can study some samples of comets or meteorites, which are actually physically coming from even beyond the solar system, but this is the very little we can collect dust of comets, etc. But those are the very limited cases in which we can do direct lab experiments. All the rest has to go through a simulation. Simulation meaning we investigate scenarios thinking we know the rules. We simulate the outcome of a given set of physical rules, and we see if it's consistent with reality. Simulations are nowadays so frequent everywhere in physics. Of course, everything we call a weather forecast simulation is a physical simulation marching in the future, the evolution of some pattern. And this is really the regime of fluidodynamics, a very complex system, a very fascinating one. If you want to design a new airplane, you need numerical simulation. If you want to simulate how buildings are reacting to earthquakes, you use numerical simulation. Now it's getting more popular these days in Italy too, but it is since forever. You simulate also what if the Vesuvio in Naples, the volcano which is there, is going to explode again, because, for example, you need to have fluidodynamics modeling the lava plumes to decide and understand which part of the town is worth evacuating and which other are basically have no chance of surviving, because, for example, you can simulate the speed of these lava plumes around the volcano slope and stuff like that. But in physics, most of the time, not always, but most of the time you try to simulate the future. What if I will build a new building? What if I will build a new airplane? What is the weather tomorrow? What if a volcano is exploding in nowadays Naples? In astrophysics, we try to simulate the past, because with telescope we can see the universe around us. If we go deeper with observation, we can access at some snapshot of the past evolution of the universe, because light takes some time to cover the distance between a past event and us. But what we do normally is to try simulate the past, because our initial condition is what we observe in the Milky Way around us or in the galaxies around us, but we don't know how all of that has formed. There are ideas, we think there is the Big Bang or some version of it, but we want to simulate past possible evolution of the universe. We can simulate, of course, march the simulation forward in the future. And I'm also interested a little bit, but if I do any prediction for how the universe would look like in 1 billion years or even 1,000 years, no one of us is going to be there to look at it. So, you know, it's not so funny to simulate something that still had to happen from the point of view of astrophysics. So the simple, I don't need to be any technical here. The way we do that is we decide important physical laws. If you want to simulate the universe, like in cosmology, you have to solve gravity, so the fact that matter is self-attracting, gas dynamics, because we have also collective effect. We have plasma in most of the universe colliding with other plasma and doing fluid dynamical events, and the space-time is expanding. All of that, we identify the rule. We find ways to write it down in computer programs. We try to make it efficient and accurate. We use analytical solution to have numerical methods consistent with reality, and then we march those codes. We solve fluid dynamics for every single cell of a simulation. We run everything starting from initial conditions. The initial conditions are coming from our best knowledge of the cosmic microwave background, which is the state of the universe roughly 300,000 after the Big Bang. We impose the ingredients, the cosmic pie chart sorted in dark matter, gas matter, dark energy, and so on, and we simulate. And then we look at digital representation of the universe. This started already from the 70s with very low resolution simulation. They already showed what we think is true even nowadays. The universe is organized in a network, the same network that we compare in this work with the human brain some years ago. First simulation just used single computer, RAM memory of just a few kilobytes. In the 70s, 1 megabyte of memory costed like $20,000. In the US, nowadays, 1 megabyte of RAM is less than a cent, and it's like what you have already in a small alarm clock. However, in the 60s, with 32 kilobytes of memory, people could fly a spacecraft to the moon. Of course, this is growing very fast. This is the supercomputer I'm using. This is hosted here just outside of Bologna. It's called Leonardo. And it is done with 50,000 computing nodes. And in total, there are like 13,000 GPUs. It's a complex parallel system. All these computers are working together. It's also burning a lot of energy. I'm telling this because very soon I'm going to establish a powerful connection between energy and computing. Every simulation is burning energy. Even if I type and I produce universes into quotes from my laptop, from a keyboard, somewhere else in the hills of Bologna, here for example, there are machines burning energy. They are getting heated up. They need to cool down. They are burning energy. This machine, Leonardo, is one of the top, in the top 10 in Europe. And it's burning every year 32 gigawatt hours per year, which is the equivalent of a city of 50,000 inhabitants. It's burning a lot of energy. We hope it is doing that for the good. For example, a few years ago, the analysis of radar crossing the Mediterranean Sea done with Leonardo helped in discovering a gas reservoir across of Cyprus in the Mediterranean Sea. So in a sense, you invest something which is energy burning a lot, like in a supercomputing center, you can also use it to understand where to find more energy in the Mediterranean Sea, for example. And it also helps to, for example, to design vaccine for COVID, just to have two of the most spectacular outcomes of simulations in the last years. Okay, if you're not familiar with astrophysics, here I collected just a few spectacular ones. This is the simulation of the probable formation of the moon. So we are simulating the past. We have these two planets. They are colliding. This is taking several centuries, I guess. Everything we are seeing here is marching very fast in time, but this is how we think the moon could have been formed. Okay, this is a simulation of the past. There were no ancestors of the moon, but we are simulating here with fluid dynamics and gravity the possible formation scenario of the moon. Or we can simulate how the Milky Way, our own galaxy, with 100 billion stars, might have been formed. This is another very famous simulation. This was being run instead in a computer center in Switzerland. And this is showing, it's covering roughly 10 billion years, and it's showing how probably the Milky Way has formed to the continuous merger after mergers of these galaxies. Some with a disk shape, some other with a more complex shape. You run the simulation, it's very beautiful. They are always very beautiful. They can be also very wrong. You try to compare with reality. Exactly in these weeks, for example, there is a debate that if you run a simulation like that and then you compute the statistics of the satellites of the Milky Way, they are not in agreement with the latest observation that shows some alignment. So people are producing new simulated version of the past and trying to see if the Milky Way forming at the end is a plausible twin of the real one or not. In the simulation we have here, you can barely resolve stars. You will never actually resolve single stars, you resolve clusters of stars. Or you go to a larger scale, you can simulate how the cosmic web has formed. This is from the Lastris simulation using another code. It's very beautiful. The simulation is very long here, but still it's trying to squeeze the entire lifetime of the universe in a few minutes. And you are seeing the formation of filaments and cluster of galaxies, and then matter will fall into them. I'm marching forward in time. Now everything is glowing in pink color, meaning active galactic nuclei has blown material outside and so on. You start forming this very beautiful structure. Okay, the simulation is evolving. You have a digital twin of the universe. At some scale, you compare it with reality. Okay. For example, the simulation is so realistic that now here, I don't know if you can see it. Here we have a real image. One of these two, you can imagine this image as two sides. One is a collection of real observations by the HST telescope, and the other is a computer simulation from the Lastris simulation. Which is which? There is no way of knowing. The reality is that the left-hand side is the real one, and the right-hand side is the simulated one. And these simulations are so realistic, not only because they look like galaxies, but they have all the properties of galaxies, or most of the properties of galaxies. You can use, for example, now you can train, Maxime is doing that among other people there, you can train detection algorithm for real galaxies using simulations to train them. You can do that with radio galaxies, many objects, because the fidelity reached by numerical simulations is very large. Okay. Now, okay, so simulations are increasing. So real simulations on Earth, or at least the simulations we know are simulation on Earth, are progressing in time in a very steady way. They are more and more energy greedy. They are now becoming increasingly more able to simulate tinier structures. So if you simulate the entire universe, until 50 years ago, it was a 2D version, and we could just clump entire galaxies together as single points. Now we are resolving stars within galaxies. In the next decade, people are going to do simulations also with planets formation within a cosmological simulation. At some point, the progression suggests we will go down and down and down in resolution. We can probably have a better understanding of all physical processes. Maybe we can simulate everything there is in the universe. What if we are part of the simulation? So this is where I was starting thinking, coming from this background. And I was interested to see if physics can help us, like, breaking the wall of this hypothesis, because in the way it is usually sold by all these people, these VIPs that sometimes speak up on the YouTube, etc., it is like it's impossible to distinguish a simulation from reality, because simulations will be able to do everything and you only perceive reality through your brain, through your feelings, your impression, there can always be a computer that can replicate it, and so there's no way to break the wall of this illusion. Can physics do it? I think it does. I think it can. This is the paper I was mentioning. So it is accepted and it will be open access in Frontiers in Physics. And now I just put it on the arXiv, so you can get the preprint version of it. And so in the last year, actually during holidays, because again, this is not my core topic, I was trying to put something quantitative in what I tried to tell to the first conference 1 year ago in my hometown. So can we use physics to test this hypothesis? Can we really say all simulations are equally possible, or having a given kind of simulation is still is it still subject to physical constraints? By the physics we know it's true, or we think it's true. So now I'm going to dive down into this paper. Is there any questions so far? I don't see any. I cannot see from here any raised hands, but if you have question, please just ask away. Otherwise, I will enter into the core.
So far, there
Yes.
were no hands
Okay,
raised. I
okay.
haven't seen. But maybe let us use this occasion. Does anybody have a question?
Do you hear me?
Yes.
An immediate?
Yeah,
Yes.
I have a question. I mean,
Yes,
you
please.
said you make a simulation,
Yeah.
and the simulation is something where you go to the past. And then if you have the simulation which you started at some point in the past, you compare it with the situation you have now. These
Yes.
were these two pictures.
Yes.
So there are always slight differences.
Yes.
And you could go with a simulation to the future, and then you would say the two simulations or the two situations you have compared now develop differently. And therefore, my problem is, what is the gain if you compare two simulations when you think of timescales which are much larger than our human time scale?
Okay.
Because we
I
never
see.
can look at simulations in the future.
Yes. Yes. I
You
see. Your
see, so
okay.
do you understand my problem?
Yes. Yes.
Yeah, okay,
yes.
thank you.
Okay, so let me recap. So paradoxically, we think we have a better understanding of the initial conditions in the universe, because the universe was very simple at the beginning. It was a perfect black body system, 300,000 after the Big Bang, and we can observe it in microwaves, and this is telling us many properties of the universe. Then we apply, for example, gravity to that system, and we see that this is collapsing and forming stars and galaxies and so on. That part of the process is non-linear, so even if you know well the initial conditions, it's not easy to march that simulation and reproduce nowadays universe. Also, in the meantime, the formation of stars, the fact that stars are exploding, the fact that you are forming complex molecules, etc., is adding complexity, which is developing over time. And already, even starting from very simple initial conditions, it's very difficult to predict how the universe will look nowadays. So, but you can do the exercise, and this exercise has been done endless time, and you can right away exclude many models because they don't look like the universe nowadays. Now, your question, I think, is, if I have two slightly different simulations that are still compatible with the universe today, what if they diverge in the future? That's a good question, because there are still non-linearities, and maybe some of these non-linearities will evolve in the future, and none of us is going to be there to tell the difference. That's a good question, but I don't think anyone is actually testing it, in the sense that you are, at the moment, if two different models or slightly different models are giving you the same solution nowadays, meaning a solution compatible with telescope observations and their uncertainties, you would say these two models are indistinguishable. Maybe I will look for another new observable to distinguish them, but I don't care. I mean, I don't march the simulation forward to see how much they would look like in the future, because usually if they show differences, those will be not in the scales of centuries, not even thousands of years. We're speaking of tens of millions years. So way, way, way far in the future. But it's a reasonable question, I guess, if I understood it.
One comment, I asked this question because the simulation, in my opinion, contains the rules, how the simulation works. And these rules are, in my opinion, the physical laws you have for the nature.
Yeah, they should. That's the
And
idea.
we are always in a position that we oversee one of the laws which also work, but have effects only in the future. So this is a problem. You do not know, even if you can come to the development as you see it today, you do not know if there is some uncovered rule which would change the simulation.
Yeah, of course, of course. It's true. We are bound just to work with the past and the present. Sadly, for astrophysical things, the future will be inaccessible. So, but it is true. There might be physical rules that are somehow hidden and that will develop or become relevant only in the future. This cannot be excluded. In a sense, dark energy, which is a very fundamental concept.
Yeah, that's what it.
Yeah, we are using in astrophysics, is getting more important over time. It got important in the last few billion years. In the future, it's supposed just to take over. And different models of dark energy maybe will produce the same evolution from the past to nowadays, and they will for sure greatly diverge in the far future, except we cannot test it. So it makes sense to work hard to kill theories and to put them to the test, having the information which is until now.
Thank you.
Okay.
Okay, so please continue. Yes, thank you.
Okay. So two key concepts we are going to use: information and energy. So there is a fundamental amount of information. Everybody of us knows it. We decide to call it the bit. So the bit is the fundamental unit of decision, which goes from a 0 to 1 or from yes to no. This is the most atomic amount of information you can imagine in logic. Yes or no. And then from that, we know that starting from that atomic definition of information, you can develop everything, because everything we call digital stems from a binary system. And if we group together 8 bits, we get a byte. Writing or flipping a bit of information anywhere requires energy. We can code a bit into flipping a coin. If we want to reverse a coin, someone has to spend some energy. If we want to change a bit in a computer, we have to spend a small amount of energy to do that physical operation. That's a very fundamental connection that was established by several people in the past. We can mention Shannon, Slizard, many people. There is always an irreducible amount of energy to flip a bit. So computation means using energy. If we are working at a given temperature, the amount of energy is at least the Boltzmann constant times the temperature times log of 2. That's a fundamental amount of energy, which we are also going to use here. Okay. Then, what is the cost of a simulation? For example, at 20 degrees Celsius, if you want to process 1 bit anywhere, 1 bit in a computer, at least you should use 10 to the minus 7 erg, which is a very small amount of energy. Okay. Just to say, the kinetic energy of a moving fly is 2 erg, and this is worth to write a megabyte. Okay, so still the amount of energy needed to write a byte or to flip a byte that someone else has written, and flipping a byte is
We don't hear you. Do you hear us? Probably also not.
Is an operation.
Hello? Do you hear us now?
Okay, and manipulating bytes energy, but to write a map of a flight, should this, okay, I hope you can hear me. It says my connection is unstable. Hello?
No, that's okay now. Thank you. That's good.
It is okay. Okay, let me go back 1 second. I was panicking. Okay. So if someone has to simulate the entire universe, what are the requirements? So the first is an incredible dynamic range. We have to simulate at least the universe we can see, that we call the observable universe, which is roughly 10 to the 26 meters, or something in the ballpark of ballpark of 50 billion light years, roughly speaking, which is the universe we can see, how far the light could reach us. The universe can also be infinite, but this is just the observable one. And then we have all this hierarchy of objects, and there are 61 orders of magnitude, which means a million of a billion, 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 billion in scale, between the largest scale and the smallest one. The smallest one in physics is called the Planck scale. It's the smallest imaginable scale, after which quantum mechanics and gravity, in a sense, have the same effect. Okay, I'm speaking very loosely, but let's say 10 to the minus 35 meter is the smallest scale we imagine could exist in physics. Okay, so that's an incredible dynamic range someone has to cover for the simulation. Then, okay, now how much information is there? It is really not easy, but luckily there is a very fundamental principle that is coming from string theory and quantum gravity. Both theories can actually be wrong, as far as I can tell. However, in the process of trying to reconcile gravity and string in the quantum level and string theory, people discover an important property that actually is more general than that, and is coming from our knowledge of black holes, that if you're not an astrophysicist, you might think they are very complex objects. They are, but the basic essence of black holes seems to be reasonably simple to handle in physics. Everything we know about black holes is implying that there is a maximum amount of information that a black hole can contain, and this is said by the holographic principle that says, if you know, and this can be generalized for every object, so if you know the radius containing an object, let's speak just about spherical object. If you know the radius containing the object, if you know how much energy is contained in the object, in the physical system, then you know how much information can be there, okay, through this formula. This is called the holographic principle. The leaders of that historically are 't Hooft or Susskind. So the important part here is that in a black hole, for example, if you add just one bit of information to the black hole, since energy is equal to mass in relativity, adding that bit of information would cause the collapse of the black hole. You cannot add more information than that. So the holographic principle is saying what is the maximum information that can be contained within a system. It's not written on stone, but it looks like a very solid physical principle, which is in agreement with what we know about black holes. What is the best we can do to guess the information content of a structure or of our universe? The important part is that this scales with surface, so radius squared, and not radius cubic, so not the volume, which is counterintuitive. It's really counterintuitive. It's called the holographic principle because you can look at it saying all the information which is within a system can be just distributed on a surface, exactly like an hologram works. An hologram is creating the illusion of a 3D system, of a 3D reality, but it's just information projected on a surface. Strictly speaking, this is saying information scales with the area containing a system and the energy, okay? Which is different from mass, for example, that scales with the volume. Okay. Now, let's use the holographic principle to bound the maximum information that can be in the universe. We get just knowing all energy which is in the universe that cosmologists know, or they think they know, and we know the size of the observable universe, we require 10 to the 24 bits. 124 bits. We can use the equivalence between information and energy, knowing the average temperature of the universe. We get that just to write that information somewhere, we need 910 to the 108 erg, which is of course a ridiculously large amount of energy. In the universe, there only is 10 to the 78 erg. So the important part here is that for systems with many particles, it is much more expensive to simulate than to have the real structure. There is much more energy required if you have to write down all the bits encoding a structure than to create the structure itself. And in the universe, we know how much energy is there, which is 10 to the 78 ergs. There are 30 orders of magnitude of difference between what is really in the universe energy-wise and what you would need to produce a digital twin of the entire universe down to the Planck scale. The holographic principle is assuming the smallest size in which you can, well, it was in the previous here, the smallest unit of entropy of information scale with the Planck length, and you take the area associated with that. So if you want to do that down to the smallest possible scale, you require this incredible amount of information. This is the maximum one. You can say it's going to be less than that. You still have 30 orders of magnitude of reduction in information before you can even approach the energy required for that. I would just say it's impossible that the entire universe is a simulation. That's the easy part. There are just 30 orders of magnitude of difference in the energy just needed to write, even to start the simulation, not even to compute it, okay? Second, now we go down with, I mean, it's fun to play the conspiracies. So, yeah, okay, but I don't believe the entire universe is a simulation. Only our planet is a simulation because we only access reality through our planet. Maybe the few astronauts that went to the moon, they were part of the simulation, or maybe, okay, the simulation is covering the distance to the moon, nothing more than that. Okay, so let's explore two cases. All our planet is simulated down to the smallest possible scale, so I would call that the full resolution scale, and everything outside of that is just some background. It requires less information to create this background that is recreating the universe, just to keep astronomers busy, essentially, but there is nothing physically there. It's a 2D simulation of some sort. Or we can have a low resolution in which we don't go down to the Planck scale that no physical experiment yet could probe. We just go down to the smallest possible resolution that would still produce no artifact in experiments. So we are still trying to keep physicists or astrophysicists busy, and we need to simulate Earth down to that smallest possible scale. So let's first look at the full resolution scale. So an easy solution, since physicists essentially are the people that are always testing the smallest scale, is that all physicists, you know, are just non-playing character in a video game. So each of them is just a digital entity which is spitting numbers, but no one actually is a real consciousness doing that measurement. But since myself, okay, I'm not working with high energy physics, but I am a physicist myself, I don't think I am a non-playing character. But this would be an easy solution, okay? Otherwise, let's apply the holographic principle to compute the maximum information you need to simulate just our planet and the people on it, of course. This gives you, using the holographic principle restricted to the energy and size of Earth, 10 to the 75 bits almost. This requires still thinking the simulation is run at the lowest possible temperature, like 1 Kelvin above absolute zero. It still requires 10 to the 59 erg of energy. How is that in a astrophysical context? This is equal to burning all the mass of all stars in a globular cluster, like Palomar 12 here. So you convert all the energy of stars into all the mass in stars into energy, or is the gravitational binding energy of a galaxy. This is just to write the simulation on a disk, not even to start the simulation. If you want to simulate, take 1,000,000 time step, you need now the energy of an entire galaxy to be dissipated. And since that amount of energy can be confined at least on something as big as a black hole, which is the maximum compressibility level, you need a supercomputer which has the size of Jupiter, and it is 10 to the 5th solar masses. And you have to burn through that computer an entire galaxy to have any decent simulation, because we want to simulate some million time step. So this looks entirely implausible to me. So you don't burn a galaxy to simulate us, I guess. However, let's say we want to be conservative. We are not sure that everywhere on Earth there is this level of detail. Maybe just below the Earth crust, everything is low resolution. I'm playing here the devil's advocate. So let's see which are the smallest scale that we should simulate, the simulator should simulate to fool scientists. So scientists, physicists have this powerful equivalence coming from quantum mechanics, which is called essentially the de Broglie wavelength. If you have something moving with a given momentum or having a given energy, you can work out the associated wavelength of it. So let's say if we know particle of a given energy and they propagate through Earth, the simulation must have a minimum cell resolution, if you want to think in terms of cell, that is equal to that. Otherwise, we will see artifact, because particles will not propagate and evolve as we know they are. We know from physical experiment. So we can say we can use we can use high energy particle accelerated in a large hadron collider in Geneva. This is giving 10 to the 13 electron volt, another energy unit used by physicists. And this would give this very short wavelength, 10 to the minus 16 centimeters. However, from space, we have much, much higher energy particle called ultra energy cosmic rays. And we know their associated wavelength is much less. It's 10 to the minus 24 centimeters, which is very far from the 10 to the minus 35 of the Planck length. Still, it's a very small one. So the simulator should somehow simulate everything down to that resolution. Okay, at least that was my reasoning. I was using cosmic ray also because the only other serious astrophysical paper dealing with that was from 2014, Constraint on the Universe as a Numerical Simulation. It was using ultra-energy cosmic rays, but okay, on extragalactic distances. They were not thinking, they were not so conspiracy-minded that they were still believing there was a space through which ultra-energy cosmic rays were propagating. Their argument was, if the simulation is much more coarse-grained than the de Broglie length of those particles, the fact that they propagate through a lattice will produce aliasing effect in the sky. Everybody working with simulation know that you can have artifact along specific axis, say the Cartesian axis of the simulation, because if you solve fluxes along the axis or diagonal to them, you can have numerical artifacts. Those are called aliasing. Those cosmic rays are observed in huge number in the sky, but they are observed to be isotropic. For the fact that no one has ever seen those kind of aliasing effect, people in that paper said, if the simulation is there, it should be more resolved than that. Okay, still using the de Broglie length. I'm more conspiracy than that because this is a fun game. We can say all the universe outside of Earth does not exist. It's a simulation. Astrophysicists are continuously fooled by a screen. And what if the inside of Earth is actually hollow, or let's say low resolution? So because those particles are just coming from the sky and then they are absorbed on the surface of our planet, we don't know what the resolution inside. No one has ever seen down to super small scale how the Earth is done. Actual measurement in geophysics are going down to the 100 meters in the interior of Earth. We are speaking here of fraction of centimeters. Luckily, to the rescue, sorry. Oops. 1 second. Now my simulation is going wrongly. I want to show you this. Okay. Actually, we have other cosmic particles that are actually going to the planet, which are high-energy neutrinos. Those are very fast particles, which are weakly interacting with matter. We know they are crossing our planet because one of the probes is in the South Pole and is observing neutrino crossing the planet. It's called IceCube. And also very recently, there was an important detection of a very high-energy neutrino, which was actually coming almost parallel to the sea. So that particular one was not crossing the planet, but all the others are. And they have a very high energy. We know they are there. We can measure. And they are associated with the wavelength of 10 to the minus 21 centimeters. So this is really the length down which we know the interior of our planet must be simulated. Otherwise, neutrinos will behave differently. Okay? And just a few minutes before connecting here, I was surprised. A colleague of mine, actually your compatriot Andriy Neronov, and we are working together. He is at this conference in Copenhagen. And you see the date, 16th of April. Someone this morning gave a talk about this particular neutrino event, and my paper ended up here this morning, and I put that on Monday. And I'm only a bit concerned about the title because the use of this neutrino at the end is to show that, no, we don't live in a simulation, I guess, but okay. Every publicity is good publicity, I guess. This was this very morning in Copenhagen. Okay, so let's follow this logic. So, okay, sorry. Everything is going bananas. 1 second. I like this tool to have the presentation, but sometimes it goes weird. Okay, so now, how to compute the new memory requirement? My proposal here was we replace the Planck constant, the Planck length, with the new smallest length that are associated with neutrino, meaning the simulation is following the same logic. I mean, the information contained is obtained still using the holographic principle, or we replace one important scale length because we're not requiring to have resolution down to the Planck length. We are happy with a coarser resolution. If we rescale this up and update the number, we get an information requirement of 10 to the 51 bit, and the energy required to write that on a disk is 10 to the 35 erg, which is more manageable. It's what the sun is emitting isotropically in 2 minutes. Of course, for us, is an incredible amount of energy, but let's say it's not so impossible to think that in 1,000 years from now, some civilization can be like a Dyson sphere, something to encapsulate and contain all the energy of a star. This is not as crazy as all the rest. So this is the energy needed to start the simulation, to write the data on disk, to represent our planet down to a low resolution. So can we say the simulation hypothesis at low resolution would work? I wouldn't say so. Some people, like this Lloyd in 2000, worked out the maximum number of operations that you can do on a bit given a given energy. This has to do with quantum mechanics. Quantum mechanics is deciding the frequency, which is the inverse of a time, associated with an energy. If you want to flip a byte with a given energy, you have physical constraints on how fast you can do this job. If you want to do that in a system which can contain the energy required to simulate the low resolution Earth, you can use the more compact system you can imagine, which is a black hole. It's going to be a super tiny one, really 10 to the minus 7 centimeters. And this black hole can process 10 to the 67, 10 to the 68 bytes per second, which is, of course, an incredible large amount of information. However, you applied to the amount of memory that you have to process continuously, you have to simulate down to 10 to the minus 32 seconds, because this is the time scale associated with the neutrino propagation. Even to simulate 1 second of our time in this reality, you need 10 to the 32 operations for every bit. That would say that at that computing rate, even for the black hole, you will take 10 million years to evolve just 1 second of the low resolution simulation, which is a lot. Who's going to spend 10 million years to evolve 1 second of our planet? You can imagine maybe someone is going to speed that up. You have to speed it up by 10 to the 17 times if you want to have at least a real-time simulation. If you want to simulate 1 second now, using 1 second of computing time in the future. if you accelerate that, you are now requiring an incredible amount of energy, which is 10 to the 73, 10 to the 75 ergs per second of power, which is what supermassive black holes are dissipating when they merge. This is happening once in the lifetime of a galaxy. You are requiring to consume the same energy at every time step of the simulation. This is just crazy. Okay. Now, since we are speaking of memory consumption and energy consumption, I need to plug my laptop to the current. 1 second. Okay, I am nearly done. I think you see where all of this is going. So nothing of this makes sense. So meaning that if we use physics, at least my version of applying physics, I mean, it's debatable, we require gigantic or just impossible amount of energies, even to start the simulation or to even evolve 1 second of the simulation. Impossible meaning they are well beyond whatever is in the universe, or gigantic meaning you have to dissipate galaxies at every second, and no one is going to do that. And by the way, moving galaxies and dissipating their energy takes billions of years, because galaxies, you don't cross a galaxy in a second. Okay, so there are so many limitations that nothing of this makes sense. So basically, I would say it is impossible that the entire universe is a simulation. It is impossible that our planet is even a low resolution simulation. There are a few interesting reactions to that. So my conclusion is that we cannot be the ancestor simulation in any possible way. Our descendant, they can be super smart. I hope we have descendant. They can be super smart. It's impossible that all Earth is simulated, even at a very low resolution, because physics is continuously probing small scales. We know they exist. If they exist in a simulation, reproducing them will require incredible amount, not incredible, impossible amounts of energy or power. Okay. Interesting way out. What if the constants in the universe where the simulation is played are different? So we are not speaking anymore of ancestor simulation of our descendant. We are speaking, can this be the simulation played in another universe, which works like our universe, but has different physical constant, like a different Newton constant, a different Planck constant, and so on. I was playing that. It was interesting because I produced in that paper a Monte Carlo set of simulations in which, in a sense, this universe that might be simulated is simulating how the real universe could be. So that's a bit of a crazy loop. But anyway, you play with constant, and just in numbers, I was trying to find the combination of the important constant ending up into the holographic principle and so on that would produce a simulation in real time, essentially. And you can end up finding combination of variables. For example, if the Hubble constant is 10 orders of magnitude less than the one we have here, or the speed of light is higher, or the Newton constant is higher, you can find combination in which this simulation, the simulation of this universe could be done. However, no idea if playing with constant in this way you can form a universe which makes sense. This was just a game, essentially. Or other possible reaction are, and this was actually initial René Descartes idea, is that the only thing you know for sure in your life is that you are conscious because you are thinking, cogito ergo sum. A thing which is very difficult to disprove or impossible is that your brain, your activity, is actually simulated by a computer, because simulating in principle a human brain just by numbers, it's a challenge, but a challenge that maybe will be solved in the next century. You require 10 to the 12 bits of memory and probably at most 10 to the 24 floating point operation per second, which is orders of magnitude in the future, but is not impossible. If you want to simulate just one brain, this is possible. Now, how to simulate one brain or just a few brains in a way in which the reality that those brains see is consistent is another problem. I would argue that if you have to simulate maybe many human beings and they are exchanging information about constant physical processes, measurement, and so on, you still have to have a simulation a background simulation, which is essentially the same of having the full Earth simulation, because we want to simulate a consistent reality in which many observers are exchanging information. So you still have to run on the side something which is as complex as an entire simulation of planet Earth. If you're just simulating a single individual, if that individual is not the person which is measuring the neutrino length, okay, it's easier to fool. So I don't think it's easy to escape from that sort of illusion instead. Or, this is also fun, the Pac-Man scenario, meaning the universe which is simulating us is entirely different. Imagine one of the creatures in the Pac-Man video game started thinking about the universe simulating it. That would be a very hard job, because you are living in 2D, you don't know gravity exists, you don't know anything about the physical constant. It's very difficult to escape the box. So if the reality simulating this universe, I'm not believing this, but this is just a philosophical conclusion, as an entirely different set of rules, is very difficult using our rules to guess the constraints in the other universe. Okay, a Pac-Man would measure energy not in joule or in erg, but in power pellets or in strawberries and so on. Okay, so my conclusion in all that is it is fun to think about that, because it's not something that you cannot discuss about. There are physical laws and they should apply. If you're speaking specifically of the ancestor simulation, our descendants are in the same universe, they should obey the same physical laws. And I think you can show this is impossible. If we are part of a simulation run in a universe with an entirely different set of physical laws, I'm not sure it's easy to show we are in a simulation, but you can still look in artifacts. All simulations that humans are producing, they have artifacts, and so far it's safe to assume every simulation will show artifacts. So there are still people looking for artifacts in pattern in nature. Or, more easy, we just don't live in a simulation and the reality is the reality. I'm curious to know what you think. I'm just taking the occasion to, say Smaczno I Paszki. And I didn't mention, I wanted to mention that before. I'm very grateful to have met Maxime, Anton, plenty of Ukrainian scientists in this year. And I'm very honored and I'm admiring all the people there that managed still to keep academia, science, and research alive amid these dreadful 3 years. I'm a bit ashamed that Europe could not do better so far to stop this mess. And I hope you will have peace and the best of luck as soon as possible. Okay, so on my side, that's it.
Thank you very much. And we are very grateful. We are very grateful that we met you today during your talk. And I must admit that many of us met your papers much before, and it was very interesting to see you in action, so to say. Here in Lviv, it was a special atmosphere. You know, your talk was shown on the screen, and in order to see it better, we switched off the light. So it was darkness, and all these nice simulated or real galaxies were here a little bit mysterious. So thank you very much.
I hope I did not. I hope I
Yeah.
did not convince anyone that we are in a simulation. When I presented this in summer last year, my son, who's 10, was there, and after the talk, he told me, but so we are part of a simulation. He got exactly the wrong message. I hope I didn't do that today.
Well, still the question remains whether it is artificial intelligence which we see on the screen or not, and other way around, you know, but let us believe that we are humans. Are there any questions? I see Yaroslav Pritula has one, please. It was by chance I saw. I see, sorry, yeah. So please raise your hands.
Nice presentation, no questions.
Yeah. Олег Петрук, please.
Добрий день, дуже цікаво. Дуже very interesting talk, very nice. It was very interesting to listen to. I may just suggest 2 improvements for your calculations. When you calculate amount of energy and resolution in time and space, which we need to make the full simulation. your calculation is based actually on the static uniform grid. But we may do this as we do actually in the hydrodynamic simulations. We may consider adaptive non-static grid. And in this case, we don't need to go to 10 minus 21 everywhere, but just for the event of the neutrino detection. This reduces a lot, and many orders of magnitude in this.
No, I understand. That means that the simulation is every time there is a neutrino, the grid is refined and de-refined. This is an interesting question. I don't know if it's easy to think reality can be the result of some mesh and to some refinement and de-refinement. In real simulation, those are causing artifacts usually. I mean, not the kind of artifacts we worry about, but if you take, I'm also using, for example, adaptive mesh refinement simulation. I know that in the way humans do that, you have some noise. Now, can we think reality is the result of something adaptive in that sense? I don't know. So essentially we are saying there is no quantum mechanics except when there is a particle hitting an observer, because still all the rest deep down we think is quantum mechanics. If we say the resolution is coarse, we are saying that everything is classical unless someone is watching, which is what quantum mechanics, okay, sometimes is actually saying, but I see your point. Okay, yeah, okay.
Now, this is argument. If we are really in a simulation, it could be a way to make the simulation.
Okay, I see your point.
So there is another question. I see it in the chat. Alexei, could you put it by voice or you want me to read it?
It is possible to apply the same approach to the concept of multiple universe. Is there any measurement possible to prove it? Ooh, okay. I'm not an expert. I think multiple universes are.
Sorry, I just had a good day. I also not expert, but I just read some articles about concept that every quantum event actually leads to multiple universe and realized in different universes. So it's like this universes multiplies every millisecond. So, and in some sense, it's also connected with simulation, because we cannot actually understand in what universe we live in.
This, as far as I understand, is going also outside of what is scientifically testable, because we don't have access to any other universe. Yeah, but I know the argument is not impossible. I mean, we don't have a strong reason why some constant in this universe have the value they have. There is an anthropic principle saying we are here because the values have the constant which are enabling conscious being to exist, etc. This can be maybe, I don't know, unwavering, can be the result of a process which has repeated itself until the right combination was there, or it is one on the infinite collection of universes, each one in a different shelf, but we don't have access to this information. So yeah, but it is related. So in a sense, if we accept the idea of a simulation, I get, so if it's the ancestor simulation, probably they are running simulation of the universe with a very specific set of laws, because our descendants are in the far future. If they can manage to have super complex simulation, they also know all the values of constant. So maybe they don't shoot infinite a number of models. They constrain the physical constant and they run one simulation. But I think I showed energetically that's impossible. Or another universe with very different physical laws, yeah, can run all possible battery of variations. And we are here because the random parameters you have in a loop somewhere have these values. Is there any way to know that? I don't think so. So we are again outside of what is scientifically provable. But yeah, it leads you there.
Thank you. If I may ask another question.
Yes, please.
So it's a bit maybe connected to machine learning probably, because imagine that you have a sensors that measure everything that you not all information you get during the day, and you measure and you record all input and all output. Is it possible to use big huge LLM to predict what you will do in next day if you know all inputs? So if yes, yeah, if answer is yes, so can we replace a person with a unknown function which we want to optimize it and just predict all? And if it's possible that maybe we don't need simulation of whole world, we need only simulation of one person, because only one person lives in simulation and everyone other are just a simulation for him. So for her. So it's
Okay.
less energy needed.
I don't know. Okay. Well, there are several people I would like to replace with a machine, but so what you're saying is you think the conscious being that is asking this question, which can be myself or yourself in this case, can be just hallucinating because it's getting inputs and outputs from some sort of machine learning algorithm. Yes, this is the digital version of Descartes' dilemma. There is also a Chinese philosopher, now I don't remember the name, who has the same. They were thinking in terms of dreams. So when you dream, you don't know you are in a dream, then you wake up, etc. So technically, yes, because the resources to keep a creature like us busy, knowing which are the constraints of the brain, are impossible to be met now, but not so far in the future. So in 100 years, in 1,000 years, there will be the resources to keep a single human brain busy with all the inputs that we gather in our daily experience. But you have to build a model of the reality outside, at least the one that a single person is accessing to. So you still have to have a very sophisticated 3D model of the environment, etc. But this is manageable because a single person is not able to probe the passage of neutrinos or any smaller scale. So this is technically doable. My argument was this can work if you want to replicate 2, 3, 4 people in the same room. If you want to escalate it to, let's say, all the people that are living in a country or in a planet, then your model needs to be so sophisticated that you run into the other energy problem. You need really to build an equivalent of the world in which there are scientists measuring constant, etc. So either you replace all scientists with non-playing characters, or you enter the same problem, I guess. That was my reasoning. But I'm really happy we're discussing, because every time I'm getting new ideas in all of that.
Are there some other questions?
Thank you. I believe it was loud, about philosopher, but okay, thank you for your.
Okay, thanks.
Are there some other questions, maybe here in the conference hall? Actually, I like these two last questions. In your answer, Franco, you used scientifically testable. That's a very good point for me. You know, when I was listening your talk, the very question whether we live in this in the simulated universe, you know, it sounds also not very, so to say, scientifically testable. In a way, you were putting the constants, not the physical constants, but constants which relate to the energy, to the size of our universe. And it was implicit assumption that somebody sitting in this universe tries to, you know, to simulate this universe. Then you take the size of this universe, the mass of this universe, you pass to Kelvin, to erg, and so on. But, well, when we are starting to play with infinities, I would say that somebody who is simulating our universe is sitting in the universe which has the same physical constants, but it is not 10 times larger, not 20 times larger, but, you know, many, many times larger. In this sense that our universe is epsilon of this big universe. So then we are touching the points which are out of natural sciences, But nevertheless, it's very interesting to discuss this because it is very pedagogical. It is we recall us and we recall other people. What is Kelvin? What is Erg? What is our universe? What is Landauer principle, and so on. So in this sense, undoubtedly, it is very interesting. But my point is that in our discussion also here, we are touching something which is, of course, beneath the field of natural sciences. Am I right in my objection, but right in my understanding of your talk?
Yes. So I started out of frustration because I didn't like the fact that, let's say, these tech guys that, I don't know, the people running Facebook and stuff, they say, yeah, all is digital, there are simulation, they can do everything. And yes, it is scientifically, you cannot dispute that empirically. However, I think you can extrapolate the physical laws to show what is doable and what is not. So it's not exactly an empirical confutation. You cannot do an experiment. Maybe someone will come up with a nice experiment to disprove we are in a simulation, but at least you can use consistency in physics to show that there are bounds and those bounds are unreasonable. So my attempt was exactly to use physics in a fun way, try to apply scientific method or some version of it to break out of this, everything we can simulate and you cannot tell it. Okay. Then, okay, if you're speaking of, so as soon as you are implying the existence of different universes, now everything becomes, I mean, super uncertain. What is the speed of light? I mean, the size of a computer scale with the speed of light in a sense. But if the speed of light is different or if there is no limitation about that in any other universe, sure, then we enter really into not even philosophy, just pure speculation. I think with these arguments, the only thing you can really kill, or at least I'm convinced myself, is you cannot be the simulation run in the same universe in the future. If you start thinking of other multiverses, etc., yes, maybe, but why should we? I mean, what's the empirical evidence of that? That was my point. But it's a very interesting crossroad of informatics, computing theory, physics, philosophy. It's nice.
Yeah. This philosophical concept of skepticism, that's something which is very related to what you told us today.
Yeah.
Thank you again. Are there any questions? If not, thank you very much for giving this talk. Thank you very much for coming virtually today in Ukraine and for being with Ukraine every day. Thank you. Goodbye.
I hope to visit in person soon, one day. Smacznej paczki. Take care. Thanks to everybody.
You're welcome.
Thank you.
Thanks to Maxine for organizing this. Take care. Goodbye.
Yeah. Thank you.
Thank you and happy Easter as well.